In the fall of 2003, one of the largest solar storms ever recorded occurred, unleashing an eruption of energy equivalent to 200 billion hydrogen bombs. This storm sent a tidal wave of superheated charged particles, traveling at speeds of up to 6 million miles an hour directly towards Earth. These storms were among the fastest, hottest, and strongest ever measured and had a significant impact on our planet. The intense energy from the sun forced astronauts on the space station to take cover in their most protected compartments. Communication streams were cut, and airliners had to be scrambled for safety. While no major damage was done, these storms served as a reminder that we are constantly at the mercy of the sun. It controls various aspects of our lives, including our climate, food production, and even our bodies. In fact, we live within the sun's atmosphere, and like other planets, we are greatly influenced by its power. There are concerns that the sun's influence is growing more powerful. Its protective boundary, which shields us from deadly cosmic rays and intergalactic winds, is gradually shrinking. The question arises, will our technology-dependent society be able to handle another solar superstorm? These storms can be so severe that they could potentially cause catastrophic effects. In 2008, NASA launched the Interstellar Boundary Explorer, IBEX, to study the effects of the sun on the farthest reaches of our solar system. IBEX joined a long list of human attempts to understand the sun's impact on our planet and our lives. The sun provides all the light and heat we need for survival. Without it, life as we know it would not exist. Studying the sun is crucial for understanding the universe and the stars within it. The sun is the closest star to us and serves as our neighborhood in the universe. We, as the planets, are like the sun's children, affected by its moods and changes. We must learn how the sun will evolve and how its constant changes affect us here on Earth. In the past 40 to 50 years, we have learned more about the sun than in all of recorded history. This golden age of exploration began in 1973 when the first manned space station, Skylab, provided us with close-up images of the sun from above Earth's atmosphere. Skylab paved the way for the current missions dedicated to studying the sun. Currently, there is a fleet of approximately 20 space probes that scan and study the sun in ways we couldn't have imagined several decades ago. By observing the sun from the vantage point of space, scientists can examine it in different wavelengths, such as X-ray and extreme ultraviolet, which reveal different temperatures and structures. These probes continuously monitor the sun, helping scientists unravel the mysteries surrounding its behavior. Some key facts about the sun. It is one of over 200 billion stars in our Milky Way galaxy and our closest, located 93 million miles away from Earth. Despite this vast distance, it takes only 8 minutes for sunlight to reach us. The sun is about 4.5 billion years old and has a lifespan of nearly 10 to 11 billion years. Although considered a medium-sized star known as a dwarf, it is massive, with a diameter of 900,000 miles. If hollowed out, approximately 1.3 million Earth-sized planets could fit inside it. The sun accounts for 99.8% of the mass in the solar system and is 300,000 times more massive than the Earth. It consists primarily of plasma, a superheated form of electrified and magnetized gas. In conclusion, studying the sun is essential for understanding its impact on our solar system and our lives. The ongoing exploration and research continue to provide valuable insights into the nature and behavior of this powerful star. The sun holds a significant position in our solar system, emphasizing the importance of understanding it. It is composed of stellar dust from billions of stars that have existed since the Big Bang, making our sun and solar system the result of generations of stars. The core of the sun is superheated, reaching temperatures of 27 million degrees Fahrenheit, generating the energy that drives its processes. Fusion occurs in the sun's core, releasing particles and light every second, equivalent to the energy produced by 1 million H-bombs. Photons, particles of light, travel through convection currents in the sun, reaching its outer layers, including the photosphere, chromosphere, and corona. The corona, the outermost layer with temperatures reaching millions of degrees, produces the solar wind, which extends beyond Pluto. The space between planets is not empty but filled with particles and rays of light. The sun's gravity pulls objects towards it, including comets that can be ripped apart by its outbursts, such as coronal mass ejections. The sun's influence extends to everything it touches, including us. Scientists rely on coincidences like total solar eclipses to study the sun, as they provide a chance to observe its outer atmosphere, the corona, which radiates energy to the edge of the solar system. Understanding the sun remains a challenge due to its immense power, but through scientific observation and missions like the Solar and Heliospheric Observatory, SOHO, we gain valuable insights into its behavior and the impact it has on our solar system. A coronagraph, similar to a natural eclipse, blocks out the blinding rays of the sun. Scientists use it to study the solar corona and answer the question of why it is significantly hotter than the sun's surface. At the sun's core, nuclear fusion converts hydrogen into helium, releasing vast amounts of energy in the form of photons, light. These photons undergo a random walk process, getting absorbed and reabsorbed multiple times before eventually leaving the sun's interior. As the photons leave, they only take 8 minutes to reach Earth. However, they leave behind a dynamic and constantly moving solar surface. The surface exhibits boiling energy, rising plasma coils called coronal loops, and dark regions known as sunspots. Sunspots, the coolest parts of the sun at around 7,000 degrees Fahrenheit, emit less light than their surroundings. Their formation is influenced by the sun's complex rotation, which creates differential rotation and intense magnetism, resulting in millions of magnetic field lines. The twisted and balled-up magnetic field lines block the convection of superhot plasma, causing sunspots to appear dark. When these magnetic field lines twist and eventually release, they create solar flares, releasing massive amounts of energy. The magnetic field lines are responsible for most theories explaining why the corona is hotter than the surface. It is believed that waves along the magnetic field bring energy from beneath the sun's surface into the corona. The solar probe Hinode, launched in 2006, studies the interaction between magnetic field lines and the corona. It recently captured images of alphane waves, which are thought to bring turbulent energy from the sun's interior to the corona. These waves cause the magnetic field lines to vibrate, leading to friction with the magnetized plasma in the corona and resulting in heating. The heat delivered to the corona radiates out into space, providing energy to the solar system. However, the sun's energy is not constant. It undergoes changes similar to Earth's seasons, and these solar seasonal changes can impact various aspects of our solar system. Day in and day out, the sun appears the same, but it actually goes through seasons known as solar minimum and solar maximum. These two distinct phases can affect our technology and potentially even our weather. During the solar minimum, there are fewer sunspots and limited solar activity. However, during the solar maximum, the sun's power increases, and there are more sunspots, flares, and coronal mass ejections. Solar flares are violent eruptions of energy that can happen quickly and release an immense amount of energy. They are like a snapping of the whip, accelerating particles close to the speed of light. On the other hand, coronal mass ejections are massive blasts that expel billions of tons of superheated gas and plasma into space. These ejections can create shock waves and are crucial for understanding space weather. Solar storms, such as the massive ones in 2003, can pose risks to astronauts and satellites. If caught off guard, solar storms can expose astronauts to significant radiation in a short period. The charged particles within coronal mass ejections can also interact with Earth's magnetic field, causing disturbances such as disruptions to satellite communication systems, radio blackouts, and interference with global positioning systems. Accurate forecasting of space weather is challenging, especially during the turbulent periods of solar maximum. Scientists strive to better understand the sun's behavior and improve their ability to predict space weather events to protect astronauts. Satellites, such as the one in 2003, can have a significant impact on Earth. They can cause power outages, surges of electrons, radio interference, and increased radiation levels. In extreme cases, solar storms can even reach power stations, leading to widespread disruptions. One of the most powerful solar events ever observed was the superflare of 1859, witnessed by astronomer Richard Carrington. This event made scientists aware of the existence of solar flares, If a similar storm were to occur today, it could potentially cause power outages for millions of people, lasting for months. The estimated economic cost could be up to $2 trillion. To better predict and understand these storms, scientists have launched space probes like the Solar Terrestrial Relations Observatory, STRDO, in 2011. These probes provide a 360-degree view of the Sun, helping scientists observe and study coronal mass ejections before they impact Earth. While solar maximum, a period of increased solar activity, can be dangerous due to space weather, solar minimum, a period of low sunspot activity, may also have its own risks. During periods of low sunspot activity, the Earth's climate can cool. In the past, prolonged periods of low sunspot activity have even been associated with lower temperatures on Earth, such as the Maunder minimum in the 17th to 18th centuries. The solar wind, another measure of solar activity, appears to be waning, which could have consequences for Earth's protection from cosmic rays. Earth's ozone layer, which shields us from harmful ultraviolet radiation, is crucial for life. If the ozone layer were significantly depleted, ultraviolet rays from the sun would reach the Earth's surface, causing severe damage to the food chain and ultimately leading to the death of life on Earth. Additionally, gamma-ray bursts, intense and brief flashes of radiation, are a potential threat. Although most gamma-ray bursts occur billions of light years away, there is a star system, the UR 104, located just 8,000 light years away, that poses a potential risk if it were to erupt. Studying the sun and its behavior is crucial to understanding and predicting these phenomena accurately. Ongoing research and advancements in technology allow scientists to gain valuable insights into the sun's activities and mitigate potential risks to our planet. One of the stars in our solar system rotates once every 8 months. However, one of these stars is on the brink of going supernova, potentially emitting a gamma-ray burst. If the beam from a gamma-ray burst were to hit Earth directly, it could pose a significant danger. The intense radiation from the burst could deplete the Earth's ozone layer by around 50% or more, as seen in a speculated ancient extinction event billions of years ago. Scientists have observed a 20% decrease in the power of the sun's solar winds over the past few decades. The solar wind, which carries the sun's magnetic field, serves as a protective barrier for the Earth against intergalactic particles. However, the shrinking and weakening of the heliosphere, the boundary where the solar wind meets intergalactic space, increases the possibility of Earth being exposed to harmful cosmic materials. The weakening heliosphere allows more cosmic rays to enter our solar system, as evidenced by the increase in high-energy electrons in Earth's vicinity. While Earth is currently protected by its thick atmosphere and magnetic field, the balance between the Sun and Earth may be further disrupted when called WR 104 emits its gamma-ray burst. Over billions of years, the Sun and Earth have developed a delicate balance necessary for life to thrive. The Sun provides the Earth with just the right amount of light, heat, and energy. This energy drives weather and climate, while plants harness it through photosynthesis to create carbohydrates that sustain life. However, increased use of fossil fuels is disrupting the balance, causing concern for the equilibrium between the Sun and Earth. In conclusion, understanding the potential risks associated with gamma-ray bursts, the weakening of the heliosphere, and the delicate balance between the Sun and Earth is vital for ensuring the safety, including fossil fuels, ultimately comes from the Sun. Fossil fuels, formed over millions of years, store ancient solar energy. Burning these fuels disrupts the balance between our planet and the Sun, leading to rising global temperatures and the greenhouse effect. While some greenhouse effect is necessary to keep Earth warm, too much can cause calamities such as melting polar caps and rising sea levels. Continued use of fossil fuels may also damage the ozone layer's ability to protect us from the Sun's harmful radiation. Maintaining a balance between the Sun and Earth requires reducing our reliance on fossil fuels and utilizing the Sun's daily energy output. The Sun emits an immense amount of energy, estimated to be 386 billion megawatts, which is equivalent to all life on Earth's energy consumption in 1 year. Efforts are underway to harness solar energy through various technologies. Solar thermal uses concentrated sunlight to generate heat and drive turbines, while solar panels directly convert sunlight into electricity. Wind turbines indirectly capture the sun's energy by harnessing wind power. Scientists are also exploring organic solar cells that mimic the process of photosynthesis, with promising results obtained from spinach molecules. To sustain the balance between Earth and the Sun, it is crucial to shift towards utilizing the Sun's abundant energy. Solar energy offers the potential to power our lives as long as the Sun continues to shine. However, it is essential to consider the future when the Sun's power becomes overly abundant, as our Sun, like other stars, will eventually meet its end in about 5 billion years. The Sun will undergo significant changes in the future. As it burns through its hydrogen and helium, it will transition into a red giant, expanding in size and filling the inner solar system. This expansion will cause the orbits of the planets to also expand outward. Instabilities in the Sun's outer atmosphere will result in the gentle ejection of its outer layers, forming glowing clouds of gas known as planetary nebulae. Ultimately, the Sun will contract into a white dwarf star, a small and compressed object about the size of the Earth. It will continue to fade and grow colder over time. The death of the Sun will have catastrophic effects on the solar system, potentially altering the orbits of nearby planets and superheating them, including Earth. The Earth's surface will be fried, and the planet may eventually become inhospitable as the Sun becomes hotter, causing the oceans to evaporate and life to cease to exist. However, all these events will occur billions of years from now, and we have time to advance our technology and explore other solar systems. Ultimately, the stardust that gave rise to Earth and its inhabitants will continue to contribute to the creation of new planets, stars, and life in the universe. The solar system we see today is the result of a turbulent past, where newborn planets battled for stable orbits. The universe can be a dangerous place. If a planet cannot establish the right equilibrium amidst the clouds of gas and dust, then its fate could be disastrous. The Curiosity rover's exploration of Mars has revealed some fascinating details into the planet's history. Its investigation of isotopes indicates that Mars formed elsewhere in the solar system and ultimately moved into our neighborhood. The solar system is filled with oddities that suggest it had an imperfect birth and malformed evolution. For example, the planets orbit the Sun in different directions. Our own planet Earth has a mysterious 23.5-degree tilt, and our moon is significantly larger than other moons relative to the size of the planet it orbits around. The grand tack hypothesis may offer some explanation for the strange and puzzling features of our solar system. Jupiter formed within a disk of gas and dust and initially moved inward towards the Sun. As it migrated, Jupiter gathered asteroids and rubble in its path, causing chaos in the inner solar system. This resulted in the destabilization of other planets, altering their orbits and causing some to be flung out or fall into the Sun. The outer solar system debris was flung inward as well. However, Jupiter's migration was eventually halted by the presence of Saturn, another gas giant lurking behind it. As Saturn grew and exerted a gravitational impact on Jupiter, their interaction became more significant than the gravity of the gaseous disk. This caused a reversal in the direction of their migration. Through the mutual push and pull of gravity, the planets synchronized their orbits, achieving a resonance. Resonances play a crucial role in the ongoing evolution in the lab, where multiple metronomes set on a swinging platform eventually synchronize their beats. As the majority of metronomes hit a beat, the platform vibrates, transferring energy to the out-of-sync metronomes, gradually bringing them into alignment. In conclusion, Jupiter's migration and gravitational interaction with Saturn brought about significant changes in the dynamics of the early solar system, leading to the formation of our planetary system and the continuing evolution we observe today. Be a force at a great distance, for example, the force of gravity, little seemingly insignificant, pushes building up over multiple cycles and have dramatic energy transfer. That is how planets do it. Like the metronomes, the two gas giants form a resonance. We don't know exactly how long that took, but we have some fiducial marks for timing in the solar system formation. And that means that the grand attack had to have occurred relatively quickly, talking hundreds of thousands of years, perhaps to a million years. The two planets retreat until they reach their current positions. The sequence of planets as we find them today is based on Jupiter and Saturn's orbits. The planets eventually achieve a sequencing that many students learn through a mnemonic, such as my very educated mother just served us 9 pizzas. Was there a time when the mnemonic was scrambled? Seems very likely. The answer is yes, not to mention a lot of additional letters were probably in there as well. Jupiter's menace of the inner solar system is finally over. If Saturn had not formed at the right time in the sufficient size, Jupiter would have continued migrating and throwing out objects, unfortunate objects in the inner solar system, and ending up very close to the sun, where it would stay. Yes, the Earth would be gone, or the Earth would have had a terrifying encounter with Jupiter and would have been at its orbit changed dramatically to gosh knows what. There's mounting evidence that Earth had a terrifying visitor, not Jupiter, but another world. Theia was essentially another proto-Earth, where there were a number of these objects flying around, and they had took time to grow. Just like the Earth, they probably had rather similar histories, and for one reason or another, the orbit of Theia was perturbed such that it collided with the Earth. It was this planetary body that was roughly the size of Mars, and through this collision, a lot of particles were ejected, probably completely destroyed. We don't really know how much of Theia was preserved. Earth is rocked off its axis surface. Liquefied chunks of Earth's mantle are shoved into space. As a planetary body of Theia ceases to exist, its remains are absorbed by the Earth and intermingled with the debris field. A new planetary body is formed. The moon, further evidence, is found in rock samples from the Apollo moon landings. This is a sample from the moon, if you can see it. This was collected by the Apollo 15 mission. Moon rocks contain isotopes identical to those found on Earth. Music. When the moon arose, it is first covered with a magma ocean. People who imagine the lunar magma ocean to be like this magnetic chamber I am describing, but at the surface and covering a whole planet. I see it as this ocean like the Pacific, but this has to be like completely magnetic orange and probably fluxing around, and probably moving. Conditions in the lunar magma are as hellish as we can imagine, but a microscopic treasure forms in the magma crystal zircons. These are the same gemstones used in jewelry, but the zircons in the Apollo moon rocks yield a different treasure. So those zircon are very important because we know they crystallize in this tuna magma ocean. We know roughly when they crystallize in the Ronald magma ocean. So they are one of these old pieces of the moon that we are looking for, one of these all P's that we can use to date the origin of the moon. Zircons not only give the age of the moon, they set a specific date for the collision. The edge of the moon is 4.51 billion years old. 4.51 billion years ago, Theia becomes part of Earth and forms the moon, but the story is not over. Space probes measure the moon slipping 3.8 centimeters further away each year. One day the moon will break free. When that day comes, there will be no more tides, no more romantic moonlit nights. Could planetary orbits be inherently unstable? Could the chaos of planetary migration return? Haute-Provence Observatory, France. It's here that a discovery from a faraway star gives one of the biggest revelations about our own solar system. The story begins when Swiss astronomers Didier Queloz and Michel Mayor noticed something unusual about a star 50 light-years away in the constellation of Pegasus. Everything about the
yellow
star
dwarf,
is
just like our
ordinary
sun,
and
but
with one strange difference. The star at Pegasus 51 is rocking back and forth. It's a weird anomaly astronomers have never seen before. They check their instruments. Everything is working, including their new spectrograph, a device that splits the starlight from Pegasus into rainbow colors. Hidden inside the colors are patterns of lines. By tracking the day-to-day movement of these lines, astronomers make a startling discovery. Pegasus 51 has a planet, but no one has ever seen a world like this. It's half the mass of Jupiter, yet it's extremely close to its star. 9 times closer than Mercury is to the sun. The planet at 51 Pegasus must be inside the corona, broiling in temperatures over 1,000,000 degrees Fahrenheit. Soon another planet is found around another star, and then another and another. Astronomers have now confirmed over 3,700 exoplanets beyond our solar system. Nearly all of them are Jupiter-class planets grazing their host star. There are new, previously unknown type called hot Jupiters. They're so numerous, hot Jupiters challenge theories about the origins of planetary systems. It's very difficult to make a planet close to the star because there isn't enough mass to build a giant planet. Very close to the star, and there's gravitational frustrations for trying to build a planet very close to start. Astronomy is shaken with a new revelation. Planets do not stay put where they're born. When they're big enough, they migrate. It's a process called planetary migration. And yet our own solar system has no hot Jupiter. Astronomers realize the Jupiter in our solar system was once on the move as well, but its migration was halted by a resonance with Saturn. Pegasus 51 shows where a planet lands when its migration is not blocked. The strongest evidence for the grand attack hypothesis comes not from our solar system, but from exo-worlds charted around other stars. Planetary migration is a universal concept. We see evidence of it out there in extrasolar planets, other solar systems. There's no reason why planet migration shouldn't have operated in our own solar system. Music, the New Horizons probe finds evidence for roving planets within our solar system while charting ancient craters on Pluto, and on the surfaces of its moons, the science team discovered many craters are the same age. This suggests that they were formed by a single event. Even way out here, tiny Pluto was smashed by a wandering planet. The Pluto catastrophe may be related to other planetary migrations in the outer solar system. Music, it was noticed that the exact orbits of the giant planets, particularly the outer giant planets, the icy planets Uranus and Neptune, can be explained by their migration outward. There's a point in time about 3.8 billion years ago where Uranus and Neptune trade, and it's because of what some of these mean motion resonance interactions that we were talking about earlier. So this mean motion resonance involving Jupiter and Saturn and so forth just causes all heck to break out in the solar system. Uranus and Neptune, all of a sudden, the 3.8 billion years, they literally swap places, and all that debris in the outer solar system gets flung inward towards the inner solar system. The disruption in the outer solar system causes a new wave of violence. Astronomers call this epic. The late heavy bombardment, much of the cratering we see on our moon today is from this period. It may be possible that swapping orbits with Uranus is how Neptune got its moon today. The epoch of planetary migration appears to be over. The solar system seems stable, but what does the future hold? Computer simulations reveal what may be the greatest threat to the solar system in over 4 billion years. It comes from a very special relationship between Jupiter and Mercury. Mercury's orbit is slowly perturbed thanks to a subtle but constant gravitational nudge from Jupiter. A new resonance like the one between Saturn and Jupiter that saved the inner solar system is forming between Jupiter and Mercury. In 2001, computer models for the solar system were run 2,500 times. Music, they plug in the positions and the orbits of all the planets in the solar system in a computer, and they just let it run through time, through millions of years, hundreds of millions of years, billions of years, to find out whether or not these orbits are stable. Change the location of one planet, say Mercury, by 1 millimeter, and you find that that change will give completely different predictions about where everything is going to be millions of years in the future. Music, to see how quickly and easily things can change, we have only to go back to our metronomes. All I have to do is stop this platform from moving so that it cannot swing freely. Now, there's no way for the metronomes to influence. They can't be going at exactly the same frequency, in the same phase, and they're just going to fall apart because they have no way of forcing the others to go to resonance. The same applies to planets. Any small change can disrupt their harmony or restore it. Now that the platform is free to swing again, it can again transfer energy and sync them up, just like we saw the first time. Scientists want to understand the consequences of a destabilized planet. Mercury, in one case, leaves the solar system. The loss of its gravitational pull disrupts the balance of both Venus and the Earth. Earth and Venus swap orbits. The superheated atmosphere of Venus cools. Massive rains pour onto the face of the desert planet. Oceans arise, the land pools, and the air thins. Even the remains of an ancient visitor begin to cool off. Venus becomes like Earth, but the reverse happens to the Earth. As Earth settles into Venus orbit, temperatures rise, the air becomes unbreathable, glaciers melt, oceans boil. The sun looms larger in the sky, only to be obscured by a thickening cloud cover. Suffering will be great but brief. The entire 4 billion year pageant of life is cooked in a matter of days. Complete and utter destruction and elimination of all life on Earth. I'm not judging in that higher life. I'm not just talking about civilization, but everything. It is the sterilization of the planet, something that I would want to think about a bit, sterilized, uninhabitable, and quiet. There is another possibility, equally dark and apocalyptic. A runaway Mercury is deflected by the gravity of Venus, barrels toward the Earth. It may be a frightening opening act of our solar system. The equilibrium of the ages is over. If this scenario is correct, Mercury crashes into the Earth, just as Theia did 4 billion years ago. The question is, could it happen today, or is it a fate far away in the future, at a time when mankind itself is but a distant memory? The problem is that even with a perfect computer that understands all of the laws of motion perfectly, not just gravity, but all the other subtle forces that go into it, you cannot give it accurate enough initial information about the locations, the masses, the sizes, the speeds of all of the objects in the solar system. Odds are we may never see such a calamity, and yet, among the billions of stars in our galaxy, how many worlds are on the move? How many will share this fate? Time is flying by on this busy, crowded planet as life changes and evolves from second to second. At the same time, the arc of the human lifespan is getting longer. 67 years is the global average, up from just 20 years in the Stone Age. Modern science provides a humbling perspective. Our lives, indeed even that of the human species, are just a blip compared to the Earth at 4.5 billion years and counting, and the universe at 13.7 billion years. It now appears the entire cosmos is living on borrowed time. It may be a blip within a much grander sweep of time. When we now ask, will time end? Our lives are governed by cycles of waking and sleeping, the seasons birth and death. Understanding time in cyclical terms connects us to the natural world, but it does not answer the questions of science. What explains Earth's past, its geological eras, and its ancient creatures? And where did our world come from? How and when will it end? In the revolution spawned by Copernicus and Darwin, we began to see time as an arrow in a universe that's always changing. The 19th century physicist Ludwig Boltzmann found a law he believed governed the flight of time's arrow: entropy. Based on the second law of thermodynamics, it holds that states of disorder tend to increase from neat, orderly starting points. The elements, living things, the Earth, the Sun, the galaxy are all headed eventually to states of high entropy or disorder. Nature fights this inevitable disintegration by constantly reassembling matter and energy into lower states of entropy in cycles of death and rebirth. Will entropy someday win the battle and put the brakes on time's arrow, or will time stubbornly keep moving forward? For answers and pawns in this cosmic conflict, we seek mastery of time's workings, even as the clock ticks down to our own certain end. Our windows into the nature of time are the mechanisms we use to chart and measure a changing universe. From the mechanical clocks of old to the decay of radioactive elements or telescopes that measure the speed of distant objects. Our lives move in sync with the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds if you're judging on its axis. It makes a series of interlocking wobbles called Milankovitch cycles. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. Plants capture it from the air or the sea. It finds its way into soils or ocean sediments as plants decay or as waste passes out of the food chain. It can take a volcanic explosion or a dramatic lowering of sea levels to release this carbon back into the air, often after millions of years. The processes that shape a planet like ours play only the smallest of roles in the evolution of the universe. To glimpse time's broader arcs, we must look to cycles that govern the larger cosmos. The reigning theory is that the universe began in a sudden expansion of space, the Big Bang. In this glorious age, the universe seeded the rich cosmic landscapes we see in our telescopes. Trillions upon trillions of stars lit up galaxies all across the cosmos. The arc of this era is defined by the life cycles of stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy release pushes outward and balances the inward force of gravity. This battle between energy and gravity is raging in stars all around the universe. But in large stars, about 10 million years after their birth, Gravity begins to gain the edge. When the mass concentrating in the core of the star reaches a critical threshold, the core collapses in on itself. The energy released in the collapse causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shock waves can cause nearby clouds of dust and gas to collapse and ignite, forming generations of smaller stars like our Sun. A byproduct of star formation, solar systems form in the collapse of the surrounding solar nebula. The life cycle of planets, especially those in close proximity, is tied to that of their parent stars. As stars like our Sun age, they grow hotter and more luminous. Billions of years from now, that will spell the beginning of the end for our home planet. As raging solar winds begin to blast away at our atmosphere, surface water will gradually disappear, rendering Earth uninhabitable. Finally, the Sun will begin to swell, growing so large that it actually envelops the Earth. Friction with the Sun's outer edges will cause this once blue world to gradually spiral inward. Unless they are large enough to go supernova, most stars end their lives in more of a whimper than a bang. Time and solar winds push their outer layers so far out they blossom and stay collects in successive generations of small stars. It will grow dimmer and dimmer. Some galaxies will see a temporary rebirth if their mass gets stirred up and combined with another. That's what's destined to happen to our Milky Way, just about the time our Sun begins to swallow our planet. Any remaining Earthlings will see the stars of the Andromeda Galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart. If it's a direct hit, the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All the turbulence of the merger could stimulate a wave of new stars being born, reinvigorating the new larger galaxy. Disclops like this, in which galactic neighbors merge, will be common as the era of stars moves into its later stages. You can see evidence of this now out in the huge voids of space between filaments of galaxies. These voids are like ever-expanding bubbles. Where the bubble walls touch, you can see filaments of galaxies. As the bubbles grow, the filaments will stretch and break, and the distance between galaxies will widen at a faster and faster pace. Eventually, no matter where you are in the universe, you will see only a few isolated clusters of galaxies huddled together with little connection to anything else and few clues to how they got there. At more distant reaches of time, tens of billions of years from now, the sky will grow darker and darker as everything recedes away from everything else. A good place to be in those long twilight years of the stellar era is a place where gravity and energy have forged an extended truce. Perhaps a place like this, not much larger than our planet Jupiter. A red dwarf is one of the smallest and dimmest stars in our universe. They have been shown to harbor planets close enough that their dim rays can sustain liquid water and life. Red dwarfs and brown dwarfs form the vast majority of stars in our galaxy. In fact, combined, their mass exceeds that of all the large stars. Because they burn so slowly, they'll be the final beacons of the majestic age of stars. An era that will extend out to 100 trillion years. Another process will begin to transform these small outposts over time. Chance encounters between objects will perturb their orbits, sending some toward the center of the galaxy and others out into the void. In this way, galaxies may gradually evaporate, with ever denser concentrations of matter accumulating in their cores. As that happens, the universe begins to take on a new character. Welcome to the degenerate era, in which the universe is populated by red and white dwarf stars steadily cooling and by the charred remains of supernova explosions, neutron stars. Even though these dead stars have used up their nuclear fuels, they continue to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Here is where cosmic evolution slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning into subatomic particles that then decay into photons. All the protons in existence date back to the early moments of the universe. Their eventual decay will mark the end of the degenerate era around a billion years after the Big Bang. That's a 1 followed by 40 zeros. Our picture of what happens after that depends on what we learn in the coming years. Beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken, 100 meters underground, The Large Hadron Collider was built to accelerate particles in opposite directions through a giant ring 27 kilometers around. When they reach nearly the speed of light, scientists will bring them into ferocious collisions. One goal is to define the final time horizons of our universe, as well as the final moments of its most persistent objects, black holes. Ranging from millions to tens of billions of times the mass of our Sun, black holes occupy the centers of large galaxies today. As those galaxies age over trillions of years of time, much of their mass will spiral toward the center and into the jaws of ever more ravenous black holes. Conceivably, these black holes could end up weighing as much as a galaxy. But when they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout our universe, particles of opposite charge constantly well up in the vacuum of space. They normally destroy each other, but when this happens at the event horizon of a black hole, one particle can be pulled in while the other escapes. This has the effect of slowly siphoning energy and mass from the whole. If this is true, even black holes are eventually doomed. However, finding out for sure is not easy. Creating a micro black hole would require more energy than any Earth-bound collider can generate, unless there is more to nature and gravity than we have thought. The key lies in whether the universe we know is part of a more complex cosmic reality beyond the three spatial dimensions plus time that we experience in our everyday lives. It is possible that our world intersects with an unseen extra dimension on an extremely tiny scale. Some scientists propose that when particles collide at very high energies, the additional gravity needed to create a micro black hole could come from this extra dimension. Scientists will know a black hole is present when they observe the shower of particles predicted by Hawking's theory. Its presence will provide a glimpse into a deeper cosmic reality while shedding light on the ultimate future of our universe. Based on Hawking's theory, a black hole observed today will take its last gasp when 10 to the 100th years have passed, a number known as a googol. Beyond that, looking to 10 to the googolplex years, if all the zeros in that number were written in tiny 1-point font, it would stretch beyond the observable universe. The question remains whether the arrow of time will have come to rest by then. Modern theories suggest that our universe is part of a larger cosmic cycle of birth and death, with new universes emerging beyond our own. The time horizons of our universe may be insignificant in the grander scheme of things. Returning to Earth, we are the products of the great era of stars and witnesses to their spectacular displays of gravity and energy. It is likely that there are other beings out there attempting to comprehend the universe, developing their own theories on its direction. However, our discoveries and theirs will eventually succumb to the entropy at work in the universe, as we all go the way of the stars. As our universe gives way to grand new sun's corona continuously. SOHO, launched in 1995, has provided valuable insights into the sun's outer atmosphere and its effects on the entire solar system. The corona, a region of the sun's atmosphere that extends millions of miles into space, is an important area of study. It is much hotter than the sun's surface, with temperatures ranging from 1 to 3 million degrees Fahrenheit. One of the main questions scientists have been trying to answer is why the corona is so much hotter than the sun's visible surface. Observing the corona during a total solar eclipse allows scientists to see this elusive region in great detail. The moon blocks out the bright light of the sun's photosphere, revealing the corona's faint and delicate structure. The observations made during these rare events have helped scientists discover plasma waves, magnetic fields, and other phenomena that play a crucial role in shaping the sun's atmosphere and driving solar activity. In addition to studying the corona, scientists also investigate the solar wind and its impact on the solar system. The solar wind is a continuous stream of charged particles that emanates from the sun and travels throughout the entire solar system. It carries energy and magnetic fields, shaping the environment and influencing the behavior of planets, comets, and other celestial bodies within its reach. By understanding how the sun's energy and particles interact with the solar system, scientists gain insights into various phenomena. Solar flares, eruptions of intense energy and particles from the sun's surface, have the potential to disrupt communication systems, damage satellites, and even pose risks to astronauts in space. Coronal mass ejections, massive explosions of plasma and magnetic fields, can also have significant impacts on Earth's magnetic field and cause geomagnetic storms. To monitor and predict solar activity, scientists rely on a network of ground-based observatories and space-based instruments. These instruments capture images of the sun in different wavelengths, allowing scientists to study various layers and phenomena occurring within the sun's atmosphere. Additionally, advanced computer models and simulations help scientists simulate and understand the complex physics involved in solar activity. As our understanding of the sun continues to evolve, so does our ability to mitigate potential risks associated with solar storms and better prepare for their impact. Early warning systems, improved space weather forecasting, and advanced technology are essential tools in ensuring the safety of our technological infrastructure and the well-being of astronauts exploring beyond Earth. Studying the sun, our nearest star, is not just a scientific endeavor, it is crucial for understanding our place in the universe. The sun's energy sustains life on Earth and influences the dynamics of the entire solar system. By unraveling the mysteries of our star, scientists gain insights into the broader workings of the cosmos and deepen our understanding of the interconnectedness of the universe. So, as we continue to explore and study the sun, let us appreciate the incredible power and beauty of our closest celestial neighbor. From its core, where fusion reactions create the light and energy we rely on, to its dynamic outer atmosphere, the sun continues to captivate and inspire scientists and astronomers around the world. The sun is the most important entity in our solar system. It is made up of the debris from many generations of stars that have lived and died over billions of years. The core of the sun is superheated to 27 million degrees Fahrenheit and is responsible for the fusion process that releases light and particles every second. The sun's outer parts consist of the photosphere, chromosphere, and corona, with each layer being progressively hotter. The sun also produces a continuous outward flow of energy called the solar wind, which extends well beyond Pluto's orbit. This space is not empty but filled with particles and rays of light. The sun's gravity holds everything in, including comets that can sometimes get directly affected by the solar wind. Scientists study the sun during total solar eclipses, which provide an opportunity to observe its outer atmosphere, known as the corona. The corona's energy reaches the edge of the solar system, covering all the planets. The Solar and Heliospheric Observatory, OHO, was built with the ability to create artificial eclipses to aid in giant paradigm shift, highlighting the significance of the sun in the solar system. Our sun, like other stars in the universe, is composed of stardust from previous generations of stars that have lived and died since the Big Bang. It serves as the primary source of power for our solar system. Deep within the sun's core, fusion reactions occur, generating immense heat of up to 27 million degrees Fahrenheit. This fusion process releases light and particles, equivalent to the energy of 1 million hydrogen bombs every second. These particles, known as photons, then travel through convection currents, traversing the radiative and convective zones of the sun before reaching its volatile outer layers. The sun's outer regions consist of three distinct components. The photosphere, often referred to as the sun's surface, isn't a solid surface like that of the Earth. Instead, it is a gaseous region with temperatures around 10,000 degrees Fahrenheit. Above the photosphere lies the chromosphere, which is counterintuitively hotter. Continuing beyond the chromosphere is the corona, the sun's outermost layer, which reaches temperatures in the millions of degrees. The sun constantly emits a flow of energy, known as the solar wind, which extends beyond Pluto, reaching a distance of 9.3 trillion miles. The space between planets is not empty, but rather filled with particles and rays of light. While the solar wind blows away from the sun, its gravity keeps everything within its reach, including comets. Occasionally, the sun's outbursts, such as coronal mass ejections, can have a dramatic impact on celestial objects like comets. Studying the sun has been challenging due to its intense output, but scientists have found a remarkable cosmic coincidence to aid their understanding: total solar eclipses. During a total solar eclipse, when the moon aligns perfectly with the sun, its photosphere is blocked, revealing the enigmatic corona, one of the hottest regions of the sun. By observing this phenomenon, scientists can gain valuable insights into the sun's outer atmosphere and its impact on the entire solar system. To capture more detailed and continuous data on the sun, engineers created the Solar and Heliospheric Observatory, (SOHO), which provides artificial eclipses by obstructing the sun's light. This has greatly facilitated the study of the sun and its complex dynamics. In conclusion, realizing the sun's importance and understanding its behavior is crucial, as it influences everything within our solar system. Continuous research and exploration will enhance our knowledge of this remarkable star. The sun represents a giant paradigm shift for us. It's the most important thing in the solar system, and we really need to understand it. Like all the other stars in the universe, our sun is made from the dust of stars that have lived and died over billions of years, going back to the Big Bang. So our sun and solar system are really the debris from many generations of stars. The sun is the solar system's main source of power. Deep in the center of our star, its core is superheated to 27 million degrees Fahrenheit and serves as the engine that drives everything else. The process of fusion is occurring inside the sun's core, releasing particles and light every second. The sun's light is made of photons, which are born in the core and propelled by convection currents through the radiative and convective zones of the sun. Eventually, they reach the volatile outer layers of our nearest star. The sun's outer parts consist of three regions: the photosphere, chromosphere, and corona. The photosphere is the surface of the sun, and it's not really a hard surface like that of the Earth. The temperature of the photosphere is around 10,000 degrees Fahrenheit. Directly above the photosphere is another thin layer called the chromosphere, which is slightly hotter than the photosphere. The temperature rises as you move away from the source of all the energy and heat, reaching millions of degrees in the third layer called the corona. The sun produces a continuous outward flow of energy called the solar wind, which carries energy out into the solar system, extending the sun's reach 9.3 trillion miles well beyond Pluto. While the solar wind blows away from the sun, it still affects everything it touches, including us. To study the sun, scientists sometimes rely on a total eclipse of the sun, which occurs when the moon is exactly aligned with the sun and blocks its photosphere. Scientists can get a good look at our nearest star through this cosmic coincidence. A total solar eclipse is a spectacular sight that grows pitch dark by thousands of times within seconds, and as the shadow sweeps across, it looks like it's coming at you at thousands of miles an hour. Scientists have used the total solar eclipse as an opportunity to study the sun's outer atmosphere, or corona, which is one of the hottest regions of the sun.